We talk a lot about large language models here,
Yeah.
and honestly, it's easy to be impressed. They handle text incredibly well, summarizing, answering questions, chatbots.
They really do. I mean, their whole design revolves around language, right? Processing text tokens, these little numerical bits representing words.
Exactly. Text in, text out. It's their bread and butter.
But that's also the catch, isn't it? Text only.
Right. What happens when the really crucial information isn't in neat paragraphs?
Hmm.
Think about graphs in reports, maybe scanned documents, even handwritten notes, or just pictures.
That's where traditional LLMs just, well, they hit a wall, they're effectively blind. They can't look at a chart and see a trend or recognize what's happening in a photo.
All that visual information, all that potentially valuable data is just
Right.
invisible to them, locked away.
It really is like trying to understand a book by only reading the text and ignoring all the illustrations and diagrams. You miss a huge part of the story.
You lose so much context, it feels incomplete.
Definitely. And to really get a handle on the information that's out there now, especially in, digital documents and online content, we need models that can handle both text and visuals.
Which brings us very neatly to what we're diving into today. We've been looking at material that tackles exactly this. It's about a fascinating class of models called vision language models, VLMs.
That's right, VLMs. And our goal for this deep dive is really to unpack them. What are they? How do they actually manage to combine seeing and reading, so to speak? What can they do?
And crucially, what are the challenges? Because like any new tech, it's not perfect, right? We'll be drawing straight from the sources we've reviewed.
Exactly. A clear-eyed look at the whole picture.
Okay, let's start at the beginning then. How is a VLM fundamentally different from the LLMs we're maybe more familiar with?
Well, the big difference is they're multimodal.
Multimodal, meaning
Correct.
multiple types of data, more than just text.
Precisely. So in this case, it means they can take both text and images as input at the same time.
Okay, they can accept both, but do they understand them together? Or is it like processing them separately?
Ah, that's the key bit. They interpret the meaning from both and, crucially, how they relate together.
So it's not just, here's a picture and here's some text. It's understanding the connection between the picture and the text.
That's the goal, yes. They process it jointly. One important thing, though, the output is usually still text.
Right. So you feed it images, maybe text and images, it figures out what's going on between them, and then it tells you about it in words.
Exactly. Text comes out at the end.
Okay, that alone sounds like it opens up a ton of possibilities. What kind of things can these VLMs actually do? What are the tasks they're good at?
Oh, quite a range. Because they combine vision and language, you get new capabilities. One big one is visual question answering, VQA.
VQA.
Oh.
Okay, what's that involve?
It's pretty much what it sounds like. You give the VLM an image, and then you ask it a question about that specific image.
So I could show it a picture of, I don't know, a park scene and ask how many dogs are in the picture? Or what's the person on the bench doing?
Exactly like that. And it's not just counting dogs, it tries to understand the context. So for your park scene, it might say, there are two dogs playing fetch, and a person on the bench is reading a book. It interprets the whole scene.
That's definitely more than just basic object recognition. It's getting into relationships and actions. Okay, what else?
Image captioning is another common one. This is where the model looks at an image and just generates a description, a sentence or two saying what's in it.
Without a specific question, you just hand it the picture.
Yep. Show it that photo of the dog catching a frisbee, and it might output something like, a golden retriever jumps to catch a blue frisbee in a grassy field. It figures out the subject, action, object setting, all from the pixels.
Okay, cool for photos. But you mentioned documents earlier, and the source material really seemed to emphasize that. How do they help there? Documents are often a mix.
Hugely important there. Document understanding is a major application. Think about things that aren't just pure text files, scanned PDFs, invoices, forms, reports.
Because they have layouts, right? Headers, columns, maybe logos or signatures, visual structure.
Exactly. Stuff a normal LLM would butcher or ignore. But a VLM, you could upload a scanned receipt, say. It uses the visual analysis to see the layout, identify the logo, find the line items, the total.
So it reads the text using OCR, but also understands where that text is and what it means based on the layout.
Right. It combines the visual structure with the recognized text. Then it can extract that data in a structured way, maybe even summarize the whole transaction for you.
That sounds incredibly useful for automating paperwork. What about charts and graphs? They're purely visual data representations.
Another key area, graph analysis. VLMs can actually look at things like bar charts, line graphs, pie charts, the kind you find embedded in reports, and understand the data they represent.
Seriously, They can look at a line graph and tell you the trend.
Yes, you could give it a sales report PDF, point it to a chart and ask, what were the sales figures for Q3? Or compare Q1 and Q2 sales.
Wow.
It would analyze that specific chart image, extract the data points from the lines or bars, interpret them, and then give you an answer in text. It's reading the visual data, not just text labels around it.
Okay, that's genuinely impressive. That leap from just processing text to interpreting visually encoded quantitative data. That's big. It must be quite a process under the hood to make that happen. How do they actually merge vision and text?
It is pretty clever, yeah. Let's walk through the mechanics based on the material. First, you have the text input, right? Your prompt.
Like asking the question, what's in this picture?
Exactly. The LLM part handles that like usual, tokenizes the words, processes them through its attention layers. Standard stuff.
Okay, familiar territory.
Right. But then comes the image, the photo, the graph, whatever. And as we said, the LLM doesn't speak pixel. It needs tokens.
So the image needs translating. How does that happen?
That's where the vision coder comes in. It's a specialized neural network whose whole job is to process that raw image.
Does it see it like we do?
Not really, no. It's more about analyzing patterns, edges, textures, colors, how things are arranged spatially. It breaks the image down into its fundamental visual features.
Like a mathematical breakdown.
Kind of. It creates a very dense numerical representation, often called a feature vector or an image embedding. Think of it as a rich numerical summary or fingerprint of the image, capturing the important visual essence.
Okay, so the image becomes this complex number fingerprint, the feature vector. But the LLM still needs tokens, not vectors. How do you bridge that gap?
Good question. That's the job of the projector. This component is absolutely crucial. It acts as a bridge. It takes the continuous feature vector from the vision encoder.
Numerical fingerprint.
Right, and it maps that vector into a sequence of discrete units, image tokens, that are in a format the LLM can understand. It's designed to resemble the format of the text tokens.
So the projector is the translator. It turns the image language of the vector into the token language that the LLM already speaks.
That's a great way to put it. It aligns the representations. It brings the image information into the same sort of conceptual space, the latent space, as the text tokens.
So now you have both. Text tokens from the prompt and these new image tokens from the picture all sort of existing together.
Exactly. They're in this unified space. And then both sets of tokens, the text ones and the image ones, are fed together into the main large language model.
Jointly, at the same time.
Yes. And the LLM's attention mechanisms, which are so powerful for understanding context and text, can now work across all the tokens. It can see how text tokens relate to other text tokens, how image tokens relate to other image tokens.
And how the text tokens relate to the image tokens, connecting the question to the picture parts.
Precisely. That's the magic. It analyzes the relationships between everything, regardless of origin, text, or image. It reasons over that combined stream.
And the result is a single text output that reflects understanding from both.
That's the idea. A caption, an answer, a summary, whatever the task was, the text output is informed by both the visual and linguistic input.
So stripping it down, VLMs basically bolt on this vision pipeline encoder plus projector to create image tokens. These get mixed with the regular text tokens, and the LLM just processes the combined sequence using its existing transformer architecture.
That's a really good summary of the core innovation, yeah. It's giving the text-based LLM a way to read images by converting them into a token format it understands.
Okay, that makes a lot of sense. It sounds incredibly powerful. But as we hinted, the material we looked at was also very clear about the challenges. It's not all smooth sailing. What are the big hurdles VLMs face?
Definitely not smooth sailing yet. There are significant limitations. One area mentioned is tokenization bottlenecks.
You said text tokenization is pretty efficient. Image tokenization, not so much.
Generally, yes. Text breaks down fairly neatly into words or parts of words. Images don't have that natural structure. Encoding all the rich detail of an image, even after the vision encoder and projector, often requires a lot more tokens compared to encoding a similar amount of information in text.
So processing an image is just heavier computationally.
It often is, yeah. It can demand more memory, more processing power, and that can make getting a response, the inference time, slower compared to just working with text.
Slower response times needs more computing power.
Okay. Now, there are techniques being developed to make it more efficient, things like perceiver resamplers trying to compress those image tokens. But fundamentally, processing dense visual data is still more intensive than text right now.
So efficiency and speed, especially with complex images or maybe videos down the line, that's a technical challenge.
Yeah.
What's another major issue?
Hallucinations. Just like we see with standard LLMs, VLMs can also hallucinate. They can generate answers or descriptions that sound perfectly reasonable but are actually wrong about the image content.
Right, the AI making stuff up problem. But now it's making stuff up about what it's supposedly seeing.
Hmm?
Why does that happen?
It goes back to how they learn. They're not truly understanding the world visually like humans do. They're learning statistical correlations from vast data sets.
Okay.
So they might see features in an image that strongly correlate with something in their training data and generate text based on that correlation, even if it's not quite right for this specific image.
Like if it sees grass and something blurry and fast, it might say dog chasing ball, because that's a common pattern, even if it's actually a cat chasing a bird.
Something like that, yes. Or misinterpreting nuanced details. The material gave an example with medical images. A VLM trained mostly on everyday internet pictures might really struggle or hallucinate when shown an X-ray or MRI if it hasn't been specifically trained on lots of medical data. It might apply general patterns inappropriately.
And I guess that risk applies to graphs and documents too. Misreading a chart.
Absolutely. Even with fine-tuning, models can sometimes misinterpret complex chart layouts or extract data points with small errors, which could lead to factually incorrect summaries or answers. Accuracy is still a major focus area.
Okay, so efficiency, speed, and accuracy hallucinations. What else? Was there a third big challenge mentioned?
Yes, bias. Bias in the training data. This plagues a lot of large-scale AI, and VLMs are no exception.
Because they're trained on huge data sets scraped from the web, often. And the web isn't exactly a perfectly balanced representation of the world.
Precisely. So if the training data, both images and the text associated with them, overrepresent certain demographics, cultures, or viewpoints, the model's understanding will inherit those biases.
The material mentioned, like Western-centric data.
Yeah, that was an example. A model trained mostly on images and descriptions from Western cultures might misinterpret or maybe even generate stereotypical descriptions for things from non-Western cultures, just because it hasn't seen enough diverse examples, or the examples it saw were biased.
So the model's worldview is skewed by its training data, leading to potential misinterpretations or unfair outcomes.
That's the risk. Mitigating this requires really careful work in curating training data sets, making them more diverse, more representative, and checking for biases. It's a huge ongoing challenge.
Okay, let's quickly recap those challenges then. 1, image processing is computationally heavy, lots of tokens, can be slow. 2, they can hallucinate, generating plausible but wrong information because they learn stats, not true understanding. 3, they inherit biases from their training data.
That sums up the main hurdles highlighted in the material pretty well. They're incredibly powerful tools, but definitely still works in progress with these significant issues to tackle.
This has been really clarifying. So pulling it all together from this deep dive, the big picture is that vision language models are giving LLMs, well, eyes, in a sense. They're enabling them to take in and reason about visual information alongside text.
Yeah, it's bridging that gap, moving towards AI that can understand information more like humans do, integrating sight and language. It's a really significant step, even with the challenges.
A very powerful evolution. It really makes you think, though, given that VLMs learn from statistical patterns, not true perception, and can hallucinate or reflect data biases, what does that really tell us about the difference between AI understanding and human knowledge? And maybe more importantly, how should that difference shape how and where we decide to actually use and trust these models going forward?